Hello, this is George Nachik. It's been about 6 months now since I first proposed this problem involving an infinite grid of resistors. To date, nobody has come up with the right answer, with the correct answer on this. I'm going to give you one last hint and wait until the end of July, and at that time I will post the solution to this problem that I had proposed. The initial question asked was, what is the equivalent resistance looking into the network between any two adjacent nodes? That particular problem was quite easy to solve because we could inject a current into a node and pull out the same current out of the other node and invoke symmetry and superposition and get the answer quite quickly. The problem that I left you with was to find the equivalent resistance looking into the network across a diagonal of one of the grids. This is a much more difficult problem to solve. In fact, it might be one of the most difficult network problems you'll ever solve. To get a handle on that is what we need to note is if I inject a current, say at node A here, I have node A, B, C, D, E, F, and G. And to make the math easy, I'm going to inject 12 amperes into node A. Now notice that we have some lines of symmetry in this network. There's one line of symmetry going through node A vertically, one horizontally, and then two on a diagonal. What I mean by symmetry is these will define lines of equal potential. You can think of this grid network as, say, being a sheet of uniform resistance. Imagine that the resistivity is uniform on this disk, and around the perimeter we have a conductor, and this is, say, an infinite sheet, and this goes out to infinity. And we inject a current, I, or 12 amps, say, in at the center, and the current will then flow outward to the perimeter uniformly. Well, at any given distance from the center, any circle centered about the injection point will be at an equal potential. We can easily see that from the symmetry. These circles will all be at the same potential. The potential difference from the injection point to any point on this perimeter will be the same. And the same holds for this network. As you can imagine that if you take a distance, a radial distance out from the injection point, say we go 2 grids over, that if I swing it, any node that we hit at that radial distance from the injection point will have the same potential. So this point, point E, this point, and this point will be at the same potential. And if, say, I go up 2 and over 1, then this point will have the same potential as this point. And then if I go over 2, up 1, that will have the same potential. Up 2, over 1, that will have the same potential. And the same thing here. There will be 8 nodes on that grid that will be at the same potential because these are all at the same radial distance away from the center. So you can define equal potential nodes in that fashion and use it to your advantage. We have, from this, we can see then that we have 4 lines of symmetry. One going vertically through the injection point, one going horizontally, and then 2 diagonals. Any node, say node B, this node and this node and this node will be at the same potential because they're the same radial distance from the injection point. Now using this symmetry, we can make some observations here on the network. At the injection point, looking outward, That's just like here. The network looks the same in all directions. So we see by symmetry that this 12 amp current is going to divide in 4 equal amounts at node A. We're going to have 3 amps flowing to the left, right, up, and down from node A. Then we can also see that this 3 amp current flowing to the right is going to split evenly going up and down by symmetry. This is a line of symmetry, so the I1 current up and down will be the same, and then we'll have a current IA that in general may be different than I1. And the same thing here. We have 3 amps flowing up. It's going to divide evenly into I1 going left and right, and then there will be some I2. Now many people have been trying to invoke symmetry at this point, which is fine. Because of symmetry, we have the currents flowing left and right being the same, but we have no guarantee that this current flowing upward is the same value. That is, that this 3 amp, what people are doing is trying to split it and say that it splits into 3 equal 1 amp currents at this point, but it doesn't. And you can see that from the symmetry. That is, in order for this current and this current and this current to be the same value, the nodes, these 3 nodes have to be at the same potential with respect to this node. Well, we can guarantee from symmetry that this node and this node are the same potential. They're the same distance, radial distance from the injection point, but this node is not. The distance from A to B is square root of 2 times 1 grid line. Okay, that's the diagonal distance, whereas the distance from the injection point up to here is 2 grid lines. This is 1.4 grid lines. This is 2 grid lines. So this potential cannot be the same as the potential here or the potential here. That being the case, then I2 cannot equal I1 because the potential difference here is different than the potential difference here. And I'll show you that now. Let's just assume that I1 and I2 are the same so that the 3 amp current flowing upward divides equally into 1 amp currents. Whenever you make these guesses, you need to check your Kirchhoff's current law and voltage laws elsewhere in the network to make sure that the values are consistent with the current and voltage laws. So let's go here. Our 12 amps now is splitting 4 ways into 3 amps. And now let's assume that this 3 amp current is now splitting equally at node C. Well, that also has to be the case here. This 3 amp current has to now split equally into 1 amp currents. Now we have a line of symmetry on this diagonal, which tells us then that this 1 amp current flowing in also has to be going outward. Those have to be 1 amp because of the symmetry here. The potential difference, the potential here and here is the same since they're the same distance away from the injection point. So the potential difference here is equal to the potential difference here, so the currents have to be the same. So if we have 2 amps flowing in, we have to have 2 amps flowing out because of Kirchhoff's current law. And if 2 amps are flowing out and these 2 currents are the same, each of those have to be 1 amp. Now, let's see what happens when we write Kirchhoff's voltage law around the loop from D, E to C, and then go D, B to C. The voltage potential difference between D and C has to be the same whether we go around this way or we go around this way. So going around D, E, C, let's call this current here I3. This is our I3 between E and D. So writing Kirchhoff's voltage law from C to D, we've got 1 amp times our resistance, well, let's just call it R, plus I3 times R, and that has to equal the potential going around counterclockwise, which is 1 times R plus 1 times R. So we see then that I3 is going to have to equal 1 ampere, solving this equation. So our I1 now has to be 1 ampere to satisfy Kirchhoff's voltage law on that grid. Well, that being the case, we know from symmetry that we have to have the 1 amp flowing that way too. Because again, we can use, see, our Kirchhoff's current law. We know that I3 is going to split 1, 1, and 1 because that's what we invoked. We say that I3 is going to split evenly 3 different ways. And because this is a line of symmetry here, we know that 1 amp going in has to have 1 amp going out. And again, if we write Kirchhoff's voltage law going from this node to this node, it has to equal going to this node since we have 1 amp times R plus 1 amp times R, or 2R. We also have to have the same going this way, so this current also has to be 1. Now, let's look at what happens here. We have, at this point, 1 amp going in and 2 amps leaving, which means then this current here has to be flowing in that direction to satisfy Kirchhoff's current law. Well, we can easily see that if we inject a current at the center of the grid, at some point in the grid, that all the currents have to flow outward to infinity. None of them can be coming back. And that's what's happened here. This current is flowing in the wrong direction in order to satisfy the condition that this 3 amp is going to split evenly. And this is the type of problem that you're going to run into. There's many other problems if you take it further. We can look at many different ways. Let me show you one other way of looking at this, is if we go let's call the current flowing this way I5. Okay. The current I4 is going to split evenly because of symmetry to the left and the right. However, the current, say I6 flowing up here, isn't necessarily going to be equal I5. Well, let's write an equation. Using Kirchhoff's voltage law from E, F, and G, we can write that I4 plus I5 is going to equal I3 plus IA. So we have I4 plus I5 is equal to I3 plus IA. Because the resistances are all equal, the resistances drop out of the voltage equation. This is Kirchhoff's voltage law on this particular loop. But remember, we just saw that I4 is a minus 1 ampere because it's flowing this way on this particular network when we say that our 3 amp current is going to divide into 3 equal 1 amp currents. It forces our I4 to be flowing towards node E from node F, so I4 is a minus 1. Our I3 here is equal to 1 ampere. We can see that here. Our I3 is 1 ampere. Now, if we want our IA to flow away from the point of injection out to infinity, IA has to be positive. We need IA to be greater than 0, which means then that I5 has to be greater than 2 amps. Let's look at what I5 is here. I5 is equal to I3 plus IA minus I4. But I4 is a minus 1. I3 is equal to 1. So putting in here, we have 2 amperes plus IA. Well, if we want IA to be positive, then obviously I5 is going to be greater than 2 amps. It has to at least be 2 amps. And then if IA is going to be greater than 0, or equal to 0, I5 is going to have to be greater than or equal to 2 amperes. Now, let's look at what happens to I6. I6, then, if we write Kirchhoff's current law at that point, we have I6, which is flowing away, plus 2I5 is got to be equal to I4. Using Kirchhoff's current law, I4 is coming into the node and it has to equal I6 plus 2I5. Well, I6 then is going to equal I4 minus 2I5. But I4, again, is minus 1. So I6 will have to equal minus 1 minus 2I5. But what is I5? I5 is at least 2 or greater. So putting in for I5, the minimum value it has to be, which is 2, this comes out to minus 5 amperes, at least, at a minimum. So I6 is going to have to be greater than the 3 amp current that's flowing in this part of the network. It's greater than the 3 amps, so that doesn't make any sense. We can't have a current out here being greater than the 3 amps that's flowing into this part of the network. So this shows you all kinds of contradictions that you end up with when you try to divide this 3 amp current into 2 or into 3 equal 1 amp currents. So that's just not going to work. Now, I'm going to give you a hint here. I'm going to give you a voltage in the network. The voltage from F to D, the voltage across between F and D is equal to 1.1155 R, where R is the value of the individual resistors in the network. This is exactly give you the exact value. The exact value for VF of D is 192 divided by pi minus 60 R. So that's the hint. I'll show you how I got that when I solve the network. But anyway, I'm giving you a voltage in the network that the voltage from F to D is this value, and from this value you should be able to compute the equivalent resistance, R equivalent, looking in across the diagonal of this network. Good luck. And now hopefully you'll see why you cannot divide this 3 amp current. At this point we lose complete symmetry. We have partial symmetry, but we don't have total symmetry at this point. Once the current divides at A and gets to node C, or this node, there's only partial symmetry. We've lost our total symmetry because we cannot say that the I2 is equal to the I1s that are branching out here. You run into trouble trying to satisfy Kirchhoff's voltage laws and current laws throughout the network. So there you go. Good luck, and post your answers to the comment section.